So, hi everyone. I will continue with the gas phase synthesis as part two, and I'll try to give you some examples of this route, and I will look into some examples from liquid phase synthesis. Gas phase synthesis, the idea is the same for almost all sorts of different routes, and that idea is the fact that atoms or molecules from which the nanoparticle to be produced are converted into vapor and nano-sized clusters and then are condensed from the vapor. So the vapor may be produced by evaporating the material, and this is analogous to water evaporating from a hot surface and condensing onto a cold surface to form tiny droplets. This method of producing nanoparticles is called gas condensation. Okay, so what I'm trying to say is let's say we want to make gold nanoparticles. We find a big chunk of gold, okay, and then we apply some sort of energy onto it, okay, and then this thing evaporates, and then you have to find a way to collect this vapor where it will form the nanoparticles on it, okay? And this is the gas condensation. This is very much similar to holding an aluminum foil a few inches above a candle, and then you will soon notice a black powder forming on it. So then congratulations, you have in fact produced nano-sized carbon nanoparticles on the foil, okay? This is very much similar to that. And so we're going to look into different versions of this general approach. The first one is called the inert gas condensation. And the whole thing here is happening in inert gas atmosphere, okay? Here, this is my inert gas inlet. In this technique, the nanopowder formed normally has the same composition as the starting material. So there is like no reaction here, no reaction, okay? You just vaporize and then condense it as the starting material. The starting material, which may be metallic, inorganic material, is vaporized inside a vacuum chamber using some source of energy. The source of energy may be in terms of heat, laser, electron beam, evaporation, and that's why all those fancy names are coming from. These processes are normally carried out in an evacuated chamber with some pressure of some inert gas like helium, okay? And this is the example that you see using a TEM for titania nanoparticles prepared by inert gas condensation. So I'm evaporating things, and that's my cold finger, okay? So you apply some cold environment where it gets condensed on top of it, and then you collect the nanoparticles here. This is where the heating is going on, where I put my sources, okay? This process is very similar to boiling a pot of water on a cold day. Water molecules that are vaporized from the pot condense a short distance above the pot, forming a mist. Similarly here, the metal atoms that boil off from the source quickly lose their energy. Here they are. They form clusters of atoms in the gas phase by nucleation. These clusters of atoms grow by adding atoms from the gas phase, and then the vapor cools rapidly here on a cold finger. A cold finger is simply a cylindrical device cooled by liquid nitrogen. Convection currents generated by heating of the inert gas by the evaporation source and by the cooling of liquid nitrogen-filled collective device carry the condensed fine powders to the collector device. Collection is going on there. The scraping or compaction processes are carried out under ultra-high vacuum conditions to obtain what you have made. The crystal size, this can be important, is dependent upon the inert gas pressure, evaporation rate, gas composition. You can control all these parameters: gas pressure, evaporation rate, gas composition. Okay, so as nano engineers, let's say, what's important for us is to be able to control my crystal size with whichever method I'm using. Extremely fine particles can be produced by decreasing either the gas pressure in the chamber or the evaporation rate, and by using light rather than heavy inert gases. So you have methods to control the particle size. Okay, this can be asked to you. I can ask, how do you control the particle size in gas phase approach with respect to liquid phase approach? Okay, so please beware of these terminologies and concepts pretty well. Nanocrystalline materials can also be synthesized by evaporating different metals from more than one evaporation source. Or you can do some rotation on the cold finger, which helps in achieving a better mixing of the vapor. Oxides, nitrides, carbides. Okay, if you don't want to get pure compounds, but some oxide nitride things of the metals can be synthesized by filling the chamber with oxygen or nitrogen. So this is a very good approach to obtain those oxide nitride nanoparticles. Okay. Thus, this method allows the synthesis of a variety of nanocrystalline materials, which is a very, very big advantage. This method is probably the only viable way to make ultra-pure metal powders. It may also be used to make compounds of metals such as metal oxides like ceramics. Since the nanopowders produced are very reactive, they're easily reacted into their oxides by introducing a small amount of oxygen into the synthesis chamber. The main problem with this method is that as the particles form, they tend to cluster and increase their size, defeating the original objective. So this is very important. As you may remember, in our last class, we had summarized what are the important parameters to obtain a nanoparticle, and one of them was to avoid agglomeration. So this thing can be a problem in this method. Okay, every method has its own ups and downs, like we talked about. That's another approach for gas phase synthesis, which is inert gas expansion. Again, we have, as you see, some evaporation sources. Okay, and then we have an inert atmosphere again, and in here we change the pressure. So evaporated atoms are carried by a high pressure helium gas stream that is expanded from a nozzle into a low pressure chamber at supersonic velocities. The adiabatic expansion of the gas leads to sudden cooling, causing the evaporated atoms to form clusters a few nanometers in diameter. As in the case of inert gas condensation, the agglomeration of nanoparticles is again is a problem requiring careful control of evaporation rate, inert gas flow. If it is these that determine the particle size and distribution, which we like, okay, to control. Or there are some other more fancier, fancy sounding approach that you can take, which is called the sonochemical processing, and you can read it from here. I'm not going to read every single line, but the idea is the same. You just change the source of your energy, let's say, to obtain these nanoparticles in different forms. So that was the main idea underlying the gas phase synthesis, okay? When we go into liquid phase synthesis, what you should focus on while looking into these different approaches is what is the controlling parameter. How do I make a nanoparticle? What is the general approach that people follow? Because once you grasp the general approach, then you can even modify it in such a way that you can make your own thing, okay, which you don't have to follow from a literature, but maybe you'll have to modify it in such a way that will suit your needs in an optimized way. Okay, So liquid phase synthesis. Nano-sized materials can often be prepared by precipitant clusters of atoms in a liquid, and this can be done in two ways. Just as crystals of salt can be made to precipitate from its solution, nanoparticles of a material can be made to precipitate from a solution. More commonly, nanoparticles are made as the product of a reaction in a liquid. So here we have a reaction in a liquid in which the particles are insoluble. Okay. Just as in gas phase, synthesis is critical to limit the size of the particle to prevent it from growing too large. And that's usually done in two main ways. The growth rate of the particle may be limited by cooling the mixture, which will stop or slow down your reaction. Okay. After the particles are formed, more commonly, the particle size is limited by, this is the second one, confining the growing particle by some method, okay? So you grow it in a little room that it can't grow anymore. That's called confining. Particle size is controlled by confining them within reversed micelle, polymer films, glasses, or zeolites, like nanoporous materials, not necessarily only zeolites. We use their empty rooms that are in nanometer sizes as reactors for confinement. Okay, the basic idea here, here meaning reverse micelle process, is quite simple. Two chemicals are chosen such that they react, to produce the material we desire. Okay, so we have A and B, that's going to give you C. If I control the entrance of B into A, then I'll control the production rate of C, for example. If the two chemicals were to be mixed on a large scale, for example, by pouring one into another, just take a glass, pour one into another, they would form large chunks or particles. So how do we make things nano? In order to make nanoparticles, it's necessary to carry out this reaction on a much smaller scale, just like oil and water. However, if they're rapidly stirred together, droplets of one phase get suspended in the other. The size of these droplets can be made very small by adding a surfactant. Okay. For example, if a small amount of water were to be mixed with a large amount of organic liquid, so water, organic liquid, and surfactant. Okay, let's say 1, 2, and 3. Small droplets of water would be formed in the organic phase. The surfactant molecules collect on the surface of the water drop and stabilize the drop. Such a droplet is termed as reverse micelle. Okay? The tiny drop is an ideal reaction chamber. Since the drop is small, only small amount of reactants can squeeze into it. When this drop reacts with the other reactant, a tiny particle, that's my compound C. Okay, that's my product, is formed. So the reverse micelle, this is the schematic of what we had summarized in here. Okay, this is my reactant A, and this is my B that is soluble in organic phase. A is soluble in aqueous phase, in water, and here is my surfactant. Okay, from a closer point of view, this is my aqueous phase, this is my organic phase. Okay, so I want this, let's say this is B and this is A. I want this B to controllably enter into my water droplet. And what is my reaction chamber? This is the whole reaction chamber, okay? And basically everything goes in a stirrer, just like that. So what I had done here is, in this process, we have two chemicals that react to produce the desired material, are chosen such that one of them is soluble in water, the other one is soluble in organic phase. So here I will have my B and then my A is already here, and these things will come together in this little chamber to produce C. That's my product. An emulsion is made by mixing a small volume of water in a large volume of organic phase, and then a surfactant is added. And the size of the water droplets are directly related to the ratio of water to surfactant. That's called VO. The surfactant collects at the interface between the water and the organic phase. If more surfactant were to be added, smaller drops would be produced, and that's how you control the size of the nanoparticle. And therefore, as will become apparent, smaller particles. Okay, so you see how we control the size of our nanoparticles and maybe the agglomeration. That's very important for our nanoparticles, are controlled in a liquid phase approach. So A is soluble in water, it's added into the mixture and it's stirred. Since it's insoluble in the organic phase, it gets uniformly distributed between the tiny droplets of water. The chemical B that's soluble in organic phase is then added to the mixture and stirred. And I form my small amounts of B, then passes through the surfactant layer, react with A, in the water drop, forming a small particle in the drop. This particle can grow only as long as there is chemical A in the drop that can react with chemical B. Since the drop is very small and contains only a very small amount of chemical A, the particle produced by the end of the reaction is very small. Thus, a nanoparticle has been synthesized and prevented from growing out of the nano regime. So this is a very good approach and very highly used one. The reverse micelle process has been used to produce a number of nanostructured materials. It's generally used to produce compounds. In some cases, nanoparticles of noble metals may be produced. And all these different various nanomaterials can be produced. In theory, nanoparticles of any material that can be produced by precipitation reaction can be made using this process. Okay. Another approach for liquid phase synthesis is called the sol gel deposition. And in sol gel deposition, the basic idea is, again, it's totally different. I mean, you have to form a network of things where the silanol groups are formed to form siloxane bridges. And in that way, you, for example, make aerogels and so on. Okay, so let's have a look at what's going on in the sol gel process. Ultrafine particles, films. Okay, so you can make nanothickness films, nanoporous membranes. You can make them all by sol gel processing. And the starting point is a solution of precursor. Precursor means my food, what I need to put in my reaction. That's the metal alkoxide solution, for example, in an appropriate solvent. The precursors are usually inorganic metals, salts, metal organic compounds such as alkoxides, metal ions with an organic ligand, okay? So if you want to make like zinc oxide nanoparticle, you have to find a metal salt of zinc in some form, okay? The precursor is subject to a polymerization reaction to form a colloidal suspension that's called the sol. Finely dispersed particles kept in suspension by adding surfactant. The suspension can be treated to extract the particles for further processing. It can be spin coated onto a substrate and so on. So you can form 3D, 2D networks of this gel. Evaporation of the solvent then leaves a dense or nanoporous film. Sol gel methods are basis for a wide variety of materials, including paints, ceramics, cosmetics, and detergents and cells. Okay, and in sol gel, you have 3 steps basically. One is, let's delete. You have, well, okay, I'll try to write it here again. The first one is the dehydration reaction or some polymerization. The second one is condensation, okay, polymerization. So things come together to form these little interesting bridges. And the third one is the drying step, okay, evaporation. So it's, if you go into a little bit deeper of what different steps you have in sol gel, dehydration, condensation, which is the polymerization part, reaction part, and the drying. Okay. And molecular self-assembly is another very highly used, very popular liquid phase synthesis approach where you need these compounds called micelles, okay, micelles, which have hydrophobic ends here. This is my hydrophobic end, and this is my hydrophilic end, which likes the water, right? Well, hydrophilic means it loves water. Hydrophobic means it doesn't like water. The idea is to create the conditions under which atoms or molecules will self-assemble into useful structures. So these things, these micelles come together by themselves. You don't do it. You just create the right environment and they come together by themselves in certain shapes and structures, driven by the minimization of their energy. The great advantage of self-assembly is that the system converges to a specific configuration without the need for further control. Okay, so if you form like a spherical micelle, then it's going to form spherical nanoparticles, or you can create something like nanowires, nanorods, and so on. The self-assembling molecules form micelles. Micelles are aggregates of amphiphilic molecules with one end that's soluble in water, the other end that rejects it. These aggregates form spontaneously at a size that depends on the concentration of the amphiphilic molecule in solution. Okay, and the center of my micelle acts as a chamber for chemical reactions and thus dictates the size of nanoparticles created. So I create my chamber myself by using this approach for my chemical reaction to produce my nanoparticle of interest that is, again, in the aimed nanoparticle size. And you can form these micelles on a film. Then you will have a 2D structure, a thin film. So self-assembly of 2D nanofilms is made possible by using Langmuir-Blodgett technique. So this is called Langmuir-Blodgett technique, which is again a technique that you should really know, at least here, be aware of. A monolayer of fatty acid is created on the surface of the water, into which a substrate is placed. Fatty acid molecules are there. The polar part locks into the water, the non-polar part rejects it. The fatty acid self-spreads across the water surface as a monolayer, and it comes into this significant arrangement. The substrate is then slowly withdrawn from the water, and it forms these micelles on it. The monolayer sticks to it and is transferred from water surface to substrate. The process allows the fabrication of single monolayers of materials as well as thicker films by repeatedly dipping and withdrawal. Okay, so it's a very, very good technique, and you can see some examples here. You can see how they created very, very nice monolayers on substrates, okay, which is extremely difficult to do. This is just one layer on the substrate, and the percent coverage is very well controlled by Langmuir-Blodgett technique. Under optimized conditions, it allows continuous tunability of particle density, spacing, even arrangement. You can have all sorts of control by this technique. And what does it do? So you can form these different nanoparticles on your film, which will, at the end, for example, if you're looking at some UV absorption spectra, you can see that those different orientations, different nanoparticles, different monofilms are giving you different results in the UV range, okay? And this is done by the silver nanomire monolayers, okay? So this is a very, very good technique. And it's very, it's pretty simple to do. You can just put it in your lab. This is like a water bath. Okay, and this is the film that you put and stick out. And by just the technique, by choosing the right composition of right chemicals and the fatty acids, you can create such a result that you see in this figure. Okay, so this was it for part 2, and I'll try to give you some more examples from these approaches in the last part of our synthesis.